Okay, now we want to talk a little bit about um, some of the accessory structures of skin, and we'll discuss first the glands. Remember, the glands in general in the body come in two forms: exocrine glands, which contain a duct, which you could think of as a hose through which the gland squirts its product into a lumen or onto its surface of some other tissue, and endocrine glands, which do not have a duct and instead actively transport their cell products directly through the cell membrane and into the bloodstream. Sebaceous glands are an example of an exocrine gland. They are holocrine, meaning that the death of secretory cells produces the actual product. This oily secretion is known as sebum, and it prevents drying and it also inhibits bacterial growth. Most of the sebum is going to empty into the hair follicle where it provides lubrication. Exceptions are in areas that are hairless, which include the lips, the meibomian glands of the eyelids, and the genitalia, as well as the skin that we find on the hair or on the palms of the hands and the soles of the feet. Sweat glands come in two types, and these are also exocrine glands. They're traditionally called apocrine and merocrine, but apocrine may secrete in a merocrine or a holocrine fashion. Merocrine or ecrine are the most common sweat glands, and they're simple coiled tubular glands that open directly onto the skin surface and as a result have their own pores, and their primary job is to regulate fluid balance and body temperature. Their coiled portion lies in the dermis, and the duct extends through the epidermis, and they produce an isotonic fluid that's mostly water. It also contains electrolytes such as sodium chloride and ammonia and urea, as well as uric acid and lactate. As it moves through the duct, the sodium chloride is moved by active transport back into the body, and the final product is hypoosmotic, and that's what we consider to be sweat. They are numerous in the palms of the hands and the soles of the feet. They're absent from the margin of the lips, the labia minora in the female genitalia region, and the tips of the penis and the clitoris. Apocrine sweat glands are active at puberty, and they're made of a coiled tubular organ that usually opens onto a hair follicle superficial to the opening of a sebaceous gland, and they secrete organic compounds that are initially odorless, but when bacteria break them down, this generates what we know as body odor. And they're found in the axillae, which of course is the area under the arms, the genitalia, which in the female would be found in the labia majora, and in the male would be the scrotum, and around the anus. Ceruminous glands are modified merocrine sweat glands that we find lining the external auditory meatus, which is basically the tunnel that leads back to the tympanic membrane, also known as the eardrum. And they secrete a product known as earwax or cerumen, which is a combination of sebum and secretions from the ceruminous glands. And what this does is, in combination with hairs, it prevents dirt and insects from entering the external auditory meatus. It keeps the eardrum supple and also retards fungal growth. Mammary glands are modified apocrine sweat glands, and their purpose, of course, is to provide nourishment for the neonate. The nails have a very interesting anatomy. The nail body is made up primarily of stratum corneum, and the eponchium or cuticle is the corneum that's superficial to the nail body, while the hypoconchium is the corneum beneath the free edge. You've probably heard that it's a good idea to push back your cuticles in order to keep your nails happy and healthy. Matrix and the nail bed are the cells that give rise to the nail. Remember that the nail itself is primarily extracellular matrix material dominated by keratin. The nail root is basically where the nail extends underneath the hypoconchium and the epiconchium into below the nail bed. This is where the nail is actually generated. Growth is continuous, unlike hair. Fingernails grow between a half a millimeter to 1 millimeter a day faster than toenails do. Now, something that's interesting, of course, about the nails is that they protect the toes and the fingertips. They are modified claws. They used to be weapons of hunting and climbing. And there are pathogens that can access the nail bed and you take advantage of the organic secretions to use as fuel. And the pathogen that I'm referring to is toenail fungus, also known as Tinea unguenum. And the way the toenail fungus makes its living is that it actually makes its way under the nail. The spores can get under the nail, and let's indicate the toenail fungus here in green. Seems like an appropriate color. And what will happen is that the spores, as they move back towards the nail bed, will begin to germinate. Okay, so you can sort of see here where we're going. Make sure I've got that plugged in. So what happens here is the spores move back. They populate the nail bed and they germinate. And as they germinate, what they do is that they lift the toenail up and out. Okay, so what will happen is that the nail will thicken. Okay, the nail will thicken as germinative filamentous fungus grows underneath. The nail will lift up, and this can cause irritation when you're wearing your footwear. Now, what we have to understand about this is that it's very difficult to get medications back here because of the poor blood supply. So even though these cells are actively producing the keratin that becomes part of the nail, the fact that we have a poor blood supply in this region has consequences. The fungus is perfectly happy to feed off of secretions and dying cells in the nail root. It's basically designed to live in areas of the body that are moist and dark, and of course rife with material for growth, and in this case it's dying tissue. So in order to treat this, we have some drugs on the market. One of them you may have heard of is Lamisil. And it's marketed as a topical, but of course the problem with applying a topical is that when you put the medication on top of the nail, very little of it absorbs through this thick keratin layer to affect the growth of the fungus. And so what we recommend instead of topical Lamisil is oral Lamisil. But the problem with this is that in order to get sufficient Lamisil to the fungal area, you have to take large amounts of this drug, so much so that it can become hepatotoxic. Which means it's bad for your liver. And so if you go on this as a prescription, generally they run blood tests if you're really trying to take this in an effort to rid yourself of the toenail fungus. Many people just opt to live with it. There is one cure, but it's rather drastic, and that's to remove the entire nail, including the nail bed, and that gives the fungus essentially nowhere to hide. But the problem, of course, then is that the toes are no longer protected. Okay, so that's an example of a pathogen finding an excellent place to make its living, where medication and conventional medical treatment are not going to be effective at accessing the pathogen. Okay, so what does the integumentary system do for us? So of course one of its most important functions is protection against abrasion. As it sloughs off, bacteria are removed in the process of desquamation. Remember that what happens as soon as the bacteria that are all around us all the time try to set up an area of infection and penetrate this outer barrier, it is shed, okay, and that's again by design. So this provides a barrier against microbes and other foreign substances. The desquamation, but also the secretions, are bacteriostatic and in some cases bactericidal, so they inhibit bacterial growth. But occasionally what will happen is that you'll get a pathogen that will penetrate this outer layer, and in the event that that occurs, the immune system is standing ready to engulf anything that passes through the epidermal layer and present it to the lymphatic system, so that we can generate now a population of lymphocytes that can effectively knock the pathogen out. The melanin, of course, guards against the mutagenic effects of UV radiation, and so this is one of the body's built-in defenses against skin cancer. The hair on the head is an insulator. It helps to retain body heat, and it's also protection against sun and abrasion. The eyebrows are basically your body's sweat bands. It keeps sweat out of the eyes. If you want to demonstrate that to yourself, shave your eyebrows off sometime and then go out and do some really hard, grueling work, and the sweat will pour into your eyes. The eyelashes protect the eyes from foreign objects such as dust and other particulates, and the hair in the nose and the ears is a barrier against particulates, insects, and other foreign matter that we don't want to have end up either in the middle or inner ear in the case of the ear, or in the respiratory system in the case of the nose. The nails protect the ends of the digits, and they're also a method of self-defense, and they can act as a barrier. The skin also acts as a barrier to water diffusion from the outside in. Remember that if your skin were like a sponge, we would constantly be changing our body's osmotic balance, and this would play havoc with our electrolyte levels and with the health of tissues and cells. So, what other components of the integumentary system provide an advantage for us in interaction with our environment? It's also a sensory organ. We can pick up the sensation of pressure, temperature, and pain, as well as hot, cold, touch, and the movement of hair. Temperature regulation is mediated by sweating and radiation. And of course, when we're cold, the blood is routed away from the integument and towards the vital organs in an effort to keep you alive. And that's what produces the white to cyanotic hue that we associate with being very, very cold. The sweat, of course, causes evaporative cooling. The arterioles in the dermis change diameter as the temperature changes. They will vasodilate when we're trying to cool the body down, and they'll vasoconstrict when we're trying to warm the body back up. And here you can see an example of how this operates. Here we have a blood vessel situated near the epidermal layer. Remember that the epidermal layer itself is avascular. It's the dermis and hypodermis that have a blood supply. What happens when the temperature goes up is that we have to cool the body back down. So what happens is that the sudiferous glands increase the rate of filtrate production, and that's where the sweat comes from. As it collects on the skin, the evaporative cooling cools the surface of the skin, and that in turn cools the blood, which in turn cools the body. In a situation where we're trying to raise body temperature, what will happen is it will have vasoconstriction at the periphery. The blood will be routed back towards the core, and the result will be that body temperature will go down less quickly, but in addition to that, we'll also initiate shivering thermogenesis in an effort to try and raise body temperature as well. So we route the blood away from the surface towards the organs, and then we begin to have our teeth chatter. What other major event happens near the skin when we're cold? Of course, the hair on our body stands up in an effort to generate a layer of dead air between the skin surface and the external environment, and that tends to hold body heat in as well. Okay, so very important. Vitamin D is critical in the mineralization of bone, and active vitamin D is a multi-step. There's a multi-step pathway that leads to active vitamin D, and one of the most critical steps occurs when UV light hits one of the vitamin D precursors. It begins in the skin and it aids in calcium absorption. Vitamin D in the form of calcitriol is essentially a mineralization hormone. It stimulates the uptake of calcium and phosphate from the intestines, and it promotes calcium and phosphate release from the bones. And so what happens here is that blood calcium levels will rise under the influence of calcitriol. It reduces calcium loss from the kidneys, and this all serves to increase plasma calcium. And you might think, okay, well, great. The only thing on the surface that I can think of that calcium is good for is mineralizing bone. But you would be wrong, because what you have to remember about calcium is it's also critical in blood clotting. It is also critical in nerve transmission, and it is absolutely a vital step in muscle contraction. And so if we don't tightly regulate our blood calcium levels, these systems will malfunction. They can shut down. So bone formation, growth and repair, blood clotting, nerve and muscle function all rely on calcium. 7-dehydrocholesterol converts to cholecalciferol when UV light hits it. The cholecalciferol is released into the blood, and then it travels to the liver and the kidneys, where it is transformed into calcitriol, and that's the active form of vitamin D. Okay, so the skin, the liver, and the kidneys, and the sun all act in order to produce this conversion. Now, where does the starting material come from? Again, it comes from our diet. Okay, we have to get the precursor in the food that we eat in order for the active vitamin D to be produced. Now, the reason that you can't just store active vitamin D on the shelf and take it in its ready to go form is because it's unstable. This is why the body seeks to generate these intermediates, because among other things, the calcitriol is photosensitive, meaning it will break down after long periods of time exposed to light, and it will also have a tendency to oxidize over time. So it's one of those things that we have to make fresh in order for it to be effective. People in cold climates and those who cover their body can be deficient in this compound, but calcitriol can also be absorbed through the intestinal wall. Again, though, it's going to be in small amounts. This is why it's consuming the precursor that is the usual pathway for making the active form of vitamin D. Sources in the diet include dairy products, liver, egg yolks, and, of course, dietary supplements. The excretion in the integumentary system is important because it regulates our fluid balance. It also serves to retard bacterial growth, and it also, in a minor way, is a method of getting rid of nitrogenous waste. Examples of waste products that are excreted through the skin include water, salt, urea, ammonia, and uric acid, but this is insignificant when compared to the amount that's eliminated by the urinary system. One of the things that we have to understand about nitrogenous waste in general, since we've already had the chapter on chemistry, we can sort of touch on this for a minute. Let's use blue. I like that color for nitrogen. So let's just look at nitrogen for a minute. Remember that nitrogen is an unusual atom. It's got 5 electrons in its outer shell and 2 in its inner. So let's draw the nitrogen atom. And there are 2 electrons in the inner shell. And those are our 5 electrons in the outer shell. So let's draw those. 1, 2, 3, 4, and over here is 5. So what you see here is that you've got 3 unpaired electrons available to form covalent bonds. This is, again, nitrogen. So what happens when nitrogen combines, for instance, say, with hydrogen, is that it'll form something we know as ammonia. But you'll have a pair of electrons that aren't participating in a covalent bond, and this pair of electrons can bind to a free proton. And remember that water is always autoionizing to some degree. Okay, there's OH minus and H plus. That represents the autoionization of water. There's H2O. And so what can happen is that we can form something called the ammonium ion. With the positive charge here on the nitrogen. And the reason this is a problem is because this causes pH to rise. And this is true of many nitrogen-containing compounds, urea and uric acid being just a couple. In, in, in the case of ammonia, which we've demonstrated here, it's obviously a strong base, but nitrogen-containing organic compounds also have this ability to scavenge protons from aqueous solution and elevate the pH. So if we don't excrete these nitrogen-containing compounds, what's going to happen is that we're going to cause the pH to go up, and that of course will play havoc with membrane potential, which will screw up muscle contraction and nerve transmission, as well as membrane potential in general in all the living cells. So we have an important task to do every day, which is to eliminate the nitrogen containing waste from our body whenever it's generated. Now, where does nitrogen containing waste come from? It comes from the breakdown of protein. And the breakdown of DNA and RNA. Okay. And in some cases, the breakdown of ATP. But the major source is protein breakdown. And if we don't get rid of this stuff, it's going to perturb the pH, and we're not going to be long for this world. You probably know that once your kidneys fail, you have to go on a procedure known as dialysis in order to keep the pH of the body close to neutral. And what dialysis does is essentially substitutes for kidney function by passing the blood through a semi-permeable membrane in the form of a long tube against a fluid that's called dialysis fluid, which is basically physiological saline. And basically the nitrogenous waste will diffuse across this semi-permeable membrane into the dialysis fluid, while the dialysis fluid is diffusing into the blood plasma, and the result is that you clean the blood plasma by dilution of the waste product. It's not a perfect system, but it can serve until a donor kidney is found. Okay, so the skin, of course, as we just noted, helps in some small way. The skin is more easily damaged because the epidermis thins as we age and the amount of collagen decreases. Skin infections become more likely because repair slows down. Wrinkling occurs due to a decrease in elastic fibers. The skin becomes drier, and that is in part due to the fact that as we age, our thirst mechanism doesn't work as well as it should, and so sometimes we don't take in enough fluid. But the skin also simply becomes drier on its own due to nothing more than cell death. A decrease in the blood supply causes a poor ability to regulate body temperature, and functioning melanocytes decrease or increase. In this, when they increase, we call these age spots. And sunlight ages the skin very, very rapidly, and that's because the UV doesn't just damage the DNA, it also can damage protein. And remember that in skin, protein is both an intracellular and an extracellular product. And if we damage it, what's going to happen is it's going to impact skin function. So here you can see an example of what happens when the skin ages as a result of increased amount of sunlight. And what you're looking at here is a couple of photos. We have an American Indian shown on the right, And we have a gentleman who appears to be from China on the left, and what you're seeing there is a difference in lifetime exposure to sun and elements, and this is what leads to, in most cases, this premature aging of the skin, as well as the normal aging process setting in on top of that. Okay, now sometimes the skin can be damaged due to chemical or thermal insult, and we call these burns. And they're classed as first, second, or third degree burns. The way that we treat full thickness burns is through skin grafts, where we split the skin and we can bring in artificial skin, or we can bring skin from cadavers, or in some cases we can do xenograft, although that's relatively rare. What we really do more often is in the event that there's not enough tissue to autograft, which is where we would take undamaged skin from one location of the body and use it to seed the area that's burned, is that we can actually do what we call xenograft. And so let's illustrate this in black. And what essentially happens with a xenograft is that we can take skin from the patient. Okay, so take patient skin, and we can graft that onto an animal called a nude mouse. So this is my little mouse here, and we'll indicate the patch of skin in red. There's our little tail. There's his eye. And let's do the patch of skin here. And so you can see where the graft begins. And what will happen over time is that this is xenografting. Is that this human skin will begin to grow, because this mouse, which is a very special kind of mouse called a nude mouse, which has no, it's been genetically engineered to have no immune system, will not reject, not moose but mouse, will not reject the transplanted skin. Then we can harvest the skin back once it's increased in surface area, and then use that to treat the burn without fear of rejection, because the original source of the skin was the patient himself, him or herself. Okay. Here you can see some examples of different types of burns. Full thickness burn shown up here. You can see that the skin is brown to black, whereas a partial thickness burn, we have sort of this strawberry yellow patchiness. Oddly enough, the full thickness burn is not as painful as the partial thickness burn, because many of the nerve endings that produce pain have been destroyed in a full thickness burn. But the danger, of course, is that we've lost this important integumentary protective covering, and in individuals that have extensive full thickness burns, we're going to have problems maintaining the homeostatic functions of the skin, such as regulating body temperature, regulating fluid balance, protecting against infection, all the stuff that we've discussed. And so this is why it's incumbent on us to try and repair the damaged area. One of the biggest problems on burn wards is massive infection and dehydration, just to name a couple. And so one of the things that we do to estimate the percentage of body burned is the rule of nines, where we estimate the amount of surface area that's been damaged as a result of thermal or chemical insult. Note that there are different proportions for the adult and child. But if we look at the adult, the head and both of the upper limbs are 9% each. The trunk is 18%, another 18% on the back. The genitals, 1%, the lower limbs, each 18%, so 9% on the front, 9% on the back. And with the child, the head is proportionally larger than the rest of the body, so 15%. The trunk, 16%, but the upper and lower limbs are pretty close to the adult um, surface area percentages. And the reason this is important is because this will prompt the clinician to use the appropriate treatment depending on the depth and the extent of the burn. So not just how deep it goes, but over how much area is covered. The other thing we have to understand about partial thickness burns is that in a partial thickness burn, if we don't damage the germinative layer of the epidermis, the skin can grow back virtually unaffected. If the partial thickness burn goes beneath the germinative layer of the epidermis, what will happen is that scar tissue can form, but if it goes all the way down through the dermal layer and into the hypodermal layer, then what we have to do is skin graft in order to repair, to have any hope of fixing the damage. And so what you're looking at here are just some different conditions that we see on the skin and their description. So you've got some normal conditions that aren't really life-threatening, and then we go into different types of infections, be they bacterial or viral, and a description of each. So start this material and know it, because it's very likely going to show up on the PRS quiz or on an upcoming exam. Okay, that's all I have to say for this podcast. I will see everybody in class. Thank you.